Okay. Hopefully people can hear us online, and thanks for people joining us in the room. So we're happy to welcome George King from the University of Michigan, who obtained his PhD from the University of Warwick in the UK in 2019, and has been working as a postdoc in Leah Corrales' group at Michigan, building and expanding on PhD research on the high energy irradiation of exoplanets and the detection of transits at novel wavelengths. So we're pleased to welcome George. I'll let you.
Listen. Yes, as Alison said, I'm George. And yes, my work sort of is at the intersection of high-energy astrophysics and exoplanets. And with the help of many of the names listed here, about some of the projects that I've been doing with some of these people the last few years. So a brief outline of what we're going to talk about. I'm going to briefly give you some background, and then I'm going to sort of go in depth on a couple of different projects, sort of split into two main sections. And we'll talk about EUV stuff. And 189, everyone's favorite. Okay, some background. So this year is 20 years since the first detection of evaporation for an exoplanet. And this is for HD 209458b, the first transiting planet detected. And the evidence for this is shown on the right. This is a transit at Lyman alpha wavelengths, which shows a depth of about 15%, so much deeper than we see transits in the optical. And the idea, the thinking here is that you have a large cloud of hydrogen gas that has been removed from your exoplanet's atmosphere. And that large amount of hydrogen then is able to block out a considerable amount of the Lyman alpha emission from the star, and so you get a much deeper transit. And the idea is that this material is at the point where it's now unbound from the planet and is streaming out into space, perhaps a comet-like tail. And we'll come back to that in a second. But the reason that this is relevant for specifically what I do a lot more with X-rays is because it is X-rays together with extreme ultraviolet that we think is driving this mass, heating the upper atmosphere of these planets and driving this material off from them. Despite the fact that the optical flux is much larger, it is these high energy wavelengths that is much more efficient at heating this region. When you put a planet really, really close into a star, the irradiation level is such that you can actually set up a hydrodynamic flow where you can drag large amounts of heavier species off as well, as opposed to the Gene's escape regime that we're on the Earth, which the Earth loses a very, very small fraction of its atmosphere. As a result. With this, we can actually drive off significant portions of exoplanet atmospheres, and in some cases, perhaps the entire envelope. And yes, on an individual system level, this is probably the most extreme transit that we've seen. This is a Neptune-sized planet, GJ436b, and its Lyman alpha transit is 56% deep, as compared to 0.7% optically. And so, yeah, the amount of hydrogen that's been stripped from this planet is very large, and it's absorbing across a huge scale. So in the schematic on the right-hand side, the solid black circle is not the planet, that's the star. That is the size of the feature that we're talking about here in terms of this comet-like tail of material streaming from the planet. And it's not just in Lyman alpha that we were able to observe this evaporation. In the last few years, the helium triplet at 1083 nanometers in the infrared has been also used to detect expanded or escaping atmospheres through deeper transits at those wavelengths. This is a metastable state of helium, and again, high energy irradiation is actually relevant here as well, even though we're talking about the near infrared, because in order to set up the metastable state, you first need to ionize the ground state with EUV. And actually, it seems that K stars in particular seem to be the most favorable stars in which to detect this feature around, because it really depends on the balance of the EUV and the mid-ultraviolet, because the mid-ultraviolet can ionize the metastable state, and you don't want to do that because then so you need enough EUV emission to ionize the ground state, but not too much that you are ionizing this metastable state. But this is all on an individual level, but we actually see the effects potentially on the population level. And all good exoplanet talks must have some sort of plot of radius versus period, or mass versus period. And so in the next two slides, I'm going to go through a couple of features that we see in the exoplanet population that are potentially driven by XUV. This first one is the Neptunian desert. This is a dearth of planets about sort of Neptune size and a little bit bigger on orbital periods of a few days. Marked here in the this triangle region here. This is the Neptunian desert. And the thinking here is that any planet that's in this region is undergoing such intense XUV irradiation that all of the atmosphere escapes, or at least enough of it to drive it then below this boundary. And so by a few gigayears, there's nothing left in this region. Very, very few planets. There's a couple in tests now that we're detecting in this region, but still very underdense compared to that. The other one that I wanted to mention is the radius gap. Radius valley, radius period valley, there's numerous names for this thing. This is a dearth of planets on 1.5 to 2 Earth radii, and also seems to, when you plot it as a function of orbital period, have this sort of negative gradient go up in period. And the thinking here is that that population of planets that you see just above the valley, these are some of the smallest planets that are able to retain a small envelope of hydrogen and helium, maybe as little as 1% by mass. And those that are below this this valley, these are stripped. Whether they don't have hydrogen and helium envelopes, if they were born with one at all. If they were, it's been stripped off by some mechanism, potentially XUV-driven escape, and at most have an atmosphere of elements like the Earth does, at most. We should acknowledge at this point that there are other proposed mechanisms for these two things. So it's not just XUV-driven escape that is able to perhaps explain some of this. For the Neptunian desert, particularly that position of the upper boundary, so if I just back the upper boundary, by which I mean could be related instead to, or the exact position of it could be instead be related to the high eccentricity migration of larger planets. The thinking being that when you go through the mathematics, you'd expect the boundary to be a little bit lower if it was just. For the radius period valley, there's a bunch of different mechanisms proposed, including stuff like different core compositions. But the other leading one, along with XUV-driven escape, is core-powered mass loss. And this is where you have the leftover heat from formation of your planet, dissipates out from the core into the atmosphere, and that actually is enough over about a gigayear to remove significant portions of the exoplanet's atmosphere. That timescale is important, and is important for my next section, because photoevaporation, at least the traditional thinking, is that this happens over very, very quickly, over 100 million years, first few 100 million years or so, post this 1 gigayear timescale, which in theory, if you get a large enough population of young planets, is one way that you can try and distinguish between them. However, that brings me on to my first main section, where we're going to look at how the EUV emission of stars evolves as they age. And the obvious starting point instead is not EUV, but X-rays, because X-rays we know a lot more about. I'll come on to why that is in a second. But the most basic way that you can think about how the X-ray emission of a star evolves over its lifetime is that you have some early period up to about 100 million years, a little bit longer for smaller stars, where the ratio of the X-ray to bolometric luminosity is essentially constant over that first period. And following that, then there is a power law decline. And this is all related to how stars spin down. That isn't to say that stars start spinning down at 100 million years. It's just that if you think about it in reverse, if you keep spinning the star up, there comes a point where you actually saturate the magnetic dynamo and you can't get any more emission out, even if you keep spinning the star up. And so in that early period, it's constant, and then once the star spins down enough, then eventually the actual activity, the emission, begins to drop off with this power law decline. And this idea, this statement that is the first 100 million years or so that is important for XUV-driven escape, holds reasonably well if our power law index here, alpha, is more negative than -1. And the way to think about this is if you think about the total integrated emission for each, I'm going to say decade of logarithmic time, by which I mean if you integrate all the emission between, say, 10 million years and 100 million years, that's going to be more than what is between 100 million years and a giga-year, and then that's more than between 1 and 10. Even though, obviously, as you're going up, you're integrating over a much wider, over a much greater period of time. And indeed, when we go out and look at this observationally, so this is one of the plots from Jackson et al. 2012, who actually split a population of FGK stars up into 7 different color bins to investigate this. But for all of those bins, they find that this slope is indeed steeper than -1. That agrees with a bunch of other studies that have been done on the last few decades. The Jackson et al. Study in particular finds this slope to be about -1.1 to -1.4, depending on which bin you're looking at. And the key thing for looking at exoplanet evolution when we model this is often assume that the extreme ultraviolet follows the same evolution with exactly the same power law. Part of the reason that we do this is actually we don't have that much information about what the extreme ultraviolet is doing. There's 2 factors for that are inextricably linked. Firstly, the extreme ultraviolet is subject to considerable absorption by the interstellar medium, particularly at the soft EUV end, as you get down towards the Lyman limit. And as a result of that, and sort of as a result of each other, there's no current facility that's able to measure the EUV emission of nearby stars. The only facility that we've had that's measured it for some nearby stars was EUVE back in the 1990s, and that gave us a very, very small handful of nearby late-type stars. So we need to extrapolate or estimate this from other means, and there's a couple of ways that you can go about doing this. You can look at stellar rotational velocities. Lyman alpha is another one, and of course, as I'm an X-ray astronomer, we'll focus on X-rays here. So in a paper in 2018, we actually went back and reapplied this method that Chadney et al. 2015 had used. This is using solar data from the Time-C mission, investigating how, for the sun, the EUV emission, or at least ratio of the EUV to X-ray emission changes as a function of this surface X-ray flux. And you find that it is a power law. Now, if you think about what I was on about a couple of slides back, where I said that we're following we assume when we're modeling exoplanet atmospheres a lot of the time, we assume that it follows the same track as the X-rays. If that were true, this ratio would be a constant. It would not change in time, or not change as you change the X-ray flux. It appears that that's not the case. The fit here on the right from our paper, the actual fit in the blue line is only to the gray points. It's fitted only to the solar data. But some of those stars that are in the bottom right corner are very, very different to our one solar type star that we fitted this relation to. Indeed, I think one of them is AU-MIC and one of them is AD-LEO. So we've got some quite active M dwarfs in the bottom right. And so even though we're only fitting to the solar data, it gives a surprisingly good estimation of what we expect the EUV. Obviously, if you want to do this, there's other ways of reconstructing where you ideally want information on both sides of the EUV, right? So you want X-rays and you want far ultraviolet lines. But for those stars where we only have X-rays, this is about the state of the art. But, so we now have two relations that I've introduced to you. The X-ray time evolution, which is a power law with alpha, and we have this power law here for how the EUV is changing with X-rays. If we combine them, we can get some estimate of what the ultraviolet does as stars age. And we end up with a relation that the ratio of the EUV and bolometric luminosities is some function of time to the power alpha multiplied by gamma plus 1. And if we substitute in our values for alpha and gamma, what we get is that for every one of those color bins that Jackson et al. 2012 was considering, EUV time evolution slope is now much shallower than this magical value of -1 that I was talking about earlier. Find values in the range of -0.6 to -0.8. Let's look at what that means graphically. So this is, again, for a solar type star. And even though the X-ray emission begins brighter, within a few hundred million years, the slower decline of the EUV means that it is dominating. And for thinking about how that's impacting exoplanets, perhaps an even more intuitive way of thinking about this is integrating this over time, or plotting a cumulative energy plot. This is the total emission in various wavelengths output by a solar type star over its lifetime. This 100 million year value is marked in the dotted vertical line. And what we see is that whereas the X-rays, it is still increasing after this point, and there is still a considerable portion after 100 million years, and there's a good reason for that I can go into in questions if you're interested. What we see for the EUV is that this is not just continuing to increase, but the rate at which it's increasing, plotted on this log axis, is continuing. And so if we think about how we can model the rate at which planets are losing atmosphere, the most basic way that we can think about this is what we call the energy-limited method, energy-limited escape. And this is just where we assume that the energy that we're putting in linearly scales with the mass loss that we get out, with some efficiency factor. And clearly, under this assumption, if we're putting way more energy in at later times, a lot more mass loss out. But as I say, this is a very basic way of looking at this. There are other things that we need to consider. We need to consider how much does the instantaneous irradiation level matter? How good is the assumption that the escape is energy limited? Maybe at later times when the irradiation level is lower, but at earlier times when the irradiation level is much higher, maybe not such a good assumption. The other things that we need to consider, the radius is going to change as you lose mass. So we think that planets, when they're first formed, have larger radii than we see at field age. There's some evidence amongst the small population of young planets that we have that is the case. And so clearly, if a radius is bigger at early times, the cross-sectional area of where we can absorb XUV emission is going to be much greater, leading to greater heating of our atmosphere. So that could then mean that the mass loss rate at early times is larger. But what it would be very interesting to see is where we go in and we model a population of planets and how they evolve as they age under XUV-driven escape. It would be interesting to see if we put this in a much shallower decline to the EUV, how much does that actually impact? And that's my sort of advice for the modelers, like, what does this do? It doesn't mean, you know, we don't perhaps know enough about the EUV to say that this is definitely what is happening, but if we put this in, what does it do? Does it change it? Does it not change it? If it doesn't change it, then it doesn't matter, but I think it's something that we need to think about. And clearly what we also want is a nice sample of young planets to explore this population in time. This is starting to discover them, but obviously we need a lot. Of course, the other implication of this is if you push the mass loss timescale, or at least the timescale on which you can strip a planet to be much longer, start running into the timescale that core-powered mass loss happens on, and then you go, can we actually use a young population in time to actually distinguish between those two mechanisms? But there are a few other things that have been proposed. Oh yeah, the other plot I just wanted to flash up as well. X-ray time evolution is, of course, also much more complicated than I've talked about. There is evidence that on a few 100 million year timescale, there's some divergence between different stars, and then only sort of once you get down to a year do they clearly a planet that is subject to the blue line here is going to have a much different evaporation history to one. That's another thing that we need to consider, and then obviously how does that then impact what the EUV. But by way of example, another project that we did last year was to apply some of this to some planets in an open cluster Praesepe. This is 670 million years old. So past this point where we expect traditionally XUV-driven escape to have finished, or not the escape to have finished, but the ability to completely strip an atmosphere has. And what we see of the total emission up to 10 gigayears that these planets will experience, to re-emphasize the point, 70% of the EUV emission is still to come ahead of them after 670 million. So I think there's 9 or 10 planets in this open cluster discovered, mostly with K2. 4 of these have archival XMM Newton observations that we analyzed last year. And I'm going to show you some plots in a second for K2-100b, which is this one, which is either in or on the edge of the Neptunian desert, depending on how you define it, and K2-104, which is down here in the green point, quite a bit. Okay, yeah, we analyzed our observations. This is the light curve for K2-100 in XMM in the blue. K2 is in red. There's a hint of maybe, you know, what would have been nice would be to have had observations back sort of here to see if this is this flare that's on the way back down. Is it an active region that's rotating out of view, therefore anti-correlated with that? There's not really enough signal. But the main thing that we then did once we'd analyzed these observations and got out estimates for what the current XUV emission is as an anchor point for the lifetime evolution is to simulate some of the features of these individuals. Under this energy limited mass loss method, and using this an empirical relation from this Chen and Rogers paper, how we're going to recalculate the radiuses. And so this is K2-100. This is this planet that's sort of on the edge of the Neptunian desert. And what we find is that although this is the first open cluster planet with a radial velocity mass measurement, it's still uncertain enough that if we're at the upper end of that range, this planet seems to be completely stable against stripping later in its lifetime. But if it's at the lower end, even though it's 670 million years old, we actually find situations where we can completely strip the planet in the future under energy limited. So re-emphasizing my point that potentially, you know, we can strip planets at a much later time, but there's obviously that we need to consider. Note the time axis difference as I switch to the next slide. So this goes up to 10 gigayears. On this one for K2-104 though now, our time axis doesn't even reach a gigayear. And this is an example of a planet that is probably already stripped, because any atmosphere that we put on it strips off very, very quickly, probably telling us that this is not a good way of because it's about 2 Earth, it's roughly 2 Earth radii. It may already have been stripped. So it is, I think, consistent with being below the valley. So this, conclusions for this section before I shift gears. So as I've said quite a few times, X-ray and EUV time evolution is often assumed the same, particularly when we're modeling the evolution of exoplanet atmospheres. But if we combine some of the empirical relations that we have for how X-rays evolve and how X-rays EUV, that implies potentially a shallower EUV slope than for X. And that then has implications for the timescale of potentially stripped planets. I'm going to shift gears, as I say. Let's talk about, instead now, a different system, HD 189733, and the idea of transits in X-rays. Quite a novel thing. But I'll start by coming back to this slide that I showed earlier for GJ436 in Lyman alpha. It's our most extreme Lyman alpha transit. And there are a handful of other Lyman alpha transits that we have, including for HD 189733. I'll do it as HD 189. This is perhaps the prototypical hot Jupiter. It wasn't the first discovered, but it is the closest transiting hot Jupiter to the Earth. It's one of the best characterized and studied planets of all exoplanets. And this is its Lyman alpha transit in the data here on the right. But that solid model and the dash model have exactly the same mass loss rate. And so this is telling, this goes and speaks to one of the limitations of looking at Lyman alpha transits. So there are some things that Lyman alpha can't tell us. To explain the difference here, think about it like this. If I remove a bunch of hydrogen gas from an exoplanet atmosphere, but I then subsequently ionize it all, suddenly all of my Lyman alpha photons that I want to be absorbed to observe a transit are going to pass straight through that hydrogen gas. Whereas clearly, if I don't ionize all that gas, if a lot of it is neutral, then it's going to be much more readily absorb that Lyman alpha and give us a much deeper Lyman alpha transit. So we cannot, from the depth of the Lyman alpha transit alone, tell what the mass loss rate is, or indeed how much hydrogen gas we have removed from the atmosphere. That's one limitation of Lyman alpha. The other main one is that we're not really sensitive to low velocity gas. The core of the Lyman alpha line is very, very readily absorbed by the interstellar medium. A lot of the work that we're doing to detect transits is in the wings of the Lyman alpha line, where we're looking at material that has been accelerated to tens of kilometers most of the time. Now, X-ray transits don't necessarily, or wouldn't necessarily, suffer from these two problems. We don't see the same level, the same scale of absorption by the interstellar medium. We're not, in X-rays, absorbing necessarily with hydrogen, rather we're absorbing with species that are also being removed from the planet, potentially. And also, well, X-rays along with the EUV is driving our mass loss, we think. So let's see what we can see at transits in those wavelengths. So what do we expect an X-ray transit to look like? Well, two images of the sun here, one in optical, one in X-rays. I hope you can tell which is which. On the left in optical, the sun, of course, has, we have this limb-darkened appearance, where the star is brightest in the center of the disk. In X-rays, this is not the case. Aside from a couple of the active regions that you see, the brightest region of emission is around the edge of the disk. The reason for this is that unlike at optical, where the emission is optically thick, in X-rays, in the corona, it's optically thin. And so the brightest region is where we're looking along the greatest column density of this coronal plasma, which just so happens to be around the edge of the disk. But this has an implication for what we expect the transit shape to look like. Because unlike in optical, where we have a very well-known sort of U-shape to our transits, at X-rays we expect this limb brightening, if you like, to give us a profile that is more W-shaped than U. So what has been done? Well, HD 189 is probably our best target for this. It's the closest transiting hot Jupiter. It's quite a deep transit. And as X-rays go, it's a relatively bright target, even though its count rate is 0.2 counts per second in XMM Newton. So back in 2013, Katja Poppenhager published a paper with 6 Chandra and 1 XMM Newton observation of HD 189, and indeed found that the count rate does indeed drop at the time of primary transit. But the signal to noise here is insufficient really to pick out the shape of the transit profile properly. And if I flick to this slide, and this is another plot from their paper in the top left now, and this is showing that the depth is actually quite uncertain. So on the left is the depth from combining all 7 observations, but on the right is all the different permutations of taking 6 of the 7 observations. So you remove one of the observations and suddenly the depth is anywhere between 2 and 9%. It's quite uncertain. So the obvious question is, can you do any better? Well, there are 20 observations now of HD 189 at primary transit with XMM Newton. This is just from one. Don't get too disappointed yet. This is only one observation of the 20. Small dip in the count rate, but it'll get better. Yeah, so the gray shaded region is the optical transit. And what do we get if we stack 143 hours of XMM Newton observations on top of each other? That's what we get. And so now, for the first time, we see this W-shaped profile that we expect for an X-ray transit. And we find that it is about 8% deep-ish from our model. An absorber that's about 4 times bigger than in the optical. And yeah, so the model for the corona that we've used is in the top right. It's a fairly simplistic view of the corona, I'll say. We're just assuming that everything is radially symmetric. It decays exponentially, and then we project it, obviously, into 2 dimensions and cover it with our absorber. And not only is this transit about 4 times deeper, it also appears to be about 20 minutes early compared to the optical. So you can see already that the duration is much longer anyway. That's partially because we have a large absorber. But the center point of that model, and indeed you can see it in the data where that highest point in the middle appears to be offset from the center of the optical transit. An obvious question to ask at this point is our ephemeris right? Well, luckily XMM Newton has simultaneous NUV coverage, and we published this paper a couple of years ago on the near ultraviolet data, and yes, it lines up perfectly with the optical. And this speaks to another project, bunch of projects that I've worked on over the last few years that I'm not going to go into too much detail today, but if you're interested, do come and talk to me, where we're trying to tease out transits from XMM Newton's optical monitor in the EUV and Swift's UVOT equivalent. They don't all look this good because we don't usually have 18 transits. But there are a few planets that have been detected in the EUV with such observations. But this gives us confidence that what we see here in terms of the timing, it does appear to be early, which then begs the question, what's going on? This is where I defer to anyone that is much better on the sort of theory and modeling side of exoplanet atmospheres than I. But some of the ideas that you could propose, do you have some sort of bow shock that's leading the planet, some sort of interaction between the planet and the star's magnetic fields, potentially? Are we just probing a completely different region of gas than you see at Lyman Alpha? You know, for some reason, is the lower velocity gas preferentially due to the interaction with the star, magnetic field, the radiation pressure, does that preferentially lead the planet for some reason? A bunch of different things that we have to see. If you have ideas, I'm all ears. But yes, so conclusions for this section. Studying X-ray transits hopefully gives us complementary information to looking at extreme transits and other wavelengths like Lyman alpha, helium, to give us more information about the mass loss that's going on from these exoplanet atmospheres, even if it can't strip a planet. Obviously, not obviously, but HD 189 is a hot Jupiter. We don't think that hot Jupiters lose their entire atmosphere over their lifetime, but they're still undergoing mass loss. They're still being irradiated. They're losing maybe as much as a couple of % of their mass over their lifetime. And so transits at these wavelengths can help tell us about what's going on for those planets. As I've shown you, we have a detected W shape for our X-ray transit. The first time that that has been done. This is the one object that we think we can do with the current generation of telescopes. There's a couple of others that we'd like to get data for to check, AUMIC, GJ436 perhaps, particularly with the deep Lyman alpha transit, but we don't expect maybe the X-ray transits to be quite as deep. And yes, this transit's early, and I've excuse me. In the last few minutes, I want to reflect on the future, both for some of the work that I'm doing now and also on a community level, what's coming. So for me, something that I've been thinking about quite a bit is looking at multi-planet systems, particularly in the context of the radius gap, the radius valley, and trying to use systems where we have planets both above and below the valley, because they have the same irradiation history, say for a scaling of r squared, and yet they have a different sort of, their atmosphere has evolved differently. Now, that could just be one's closer, so it strips quicker. But there are a few systems whose architecture, for instance, K23, look at Hannah Diamond Lowe's paper from last year on that. There are a few systems where the architecture is not consistent with XUV-driven escape. And clearly those handful of systems are systems that we're going to have to explain if we think XUV-driven escape is the dominant mechanism for stripping atmospheres. Or, maybe if it's similar level to core powered mass loss. So there's definitely systems that we're going to have to explain, and that we're finding both with Kepler, with TESS, and each time we get more systems that we can test like this. But yeah, I have a paper in review where we've looked at a couple more systems with planets either side of the radius valley. We find them so far. This paper's in review, and I think it'll be quite an extensive review, but so far we've found that the planets are consistent, though, with XUV-driven escape. Building a much bigger sample of these kinds of is another way that we can probe this. Something else that I'm looking at the moment, and I just wanted to flash this up because I think it's cool. This is DS-TUC, which is a 45 million year old system, and this is just to show the difference between our current generation of X-ray telescopes and what they're all good at. So XMM Newton has a very good effective area compared to Chandra, but for DS-TUC, which has a binary companion at 5 arc seconds, it's very, very difficult to tease out or separate the two stars. We had 4 observations in Chandra last year, as shown on the right, and we are able to stars up really nicely. So look out for this paper coming soon where we characterize the X-ray emission of or the X-ray radiation of the planet, hopefully a little bit better, and also there's some interesting stellar X-ray astrophysics that we can, because we have 4 observations and trying to see how these two stars vary within the saturation period. Again, I can go into more detail if anyone. And then the very final thing is just on a sort of larger scale, we have a bunch of facilities, hopefully, well, proposed and hopefully some of them coming online in the next 10, 15 years. There's XRISM launching hopefully later this year. I don't know off the top of my head how good that's going to be for stellar astrophysics, but it is going to be another instrument in small but powerful array of X-ray telescopes. There's AXIS that both myself and Leah Corrales, my boss, are involved with in the Stellar Working Group, and trying to figure out how we can optimize AXIS to do some cool stellar X-ray astronomy and, by extension, some standard astronomy. And of course, the big question is Athena. We hope it will fly. We hope it will fly in its current configuration, because the effective area increase that we will get from it is big, and we can hope to maybe then probe a couple more X-ray transits with it, because we'll have a lot more photons to play with. But that's sort of the general direction of what we're hoping for coming online soon. There's probably other X-ray telescopes, but these are the ones that are sort of on my mind at the moment. And yeah, that's basically it. I've sort of reiterated these points at the end of the main two sections of my talk, so I won't labor them any further, other than to say thank you very much for coming along today. Thank you for your attention, and I'll take any questions. Thank you.
Okay, perfect. Yeah, so if there are questions online, feel free to put them in the chat or raise your hand. The claps, virtual claps. Yeah, we'll have a question in the room from Vladimir.
Thank you for a very interesting presentation. Yeah, I'm really excited to see the W-shaped X-ray transit that presents really challenge for theoretical modeling, and will definitely provide these good constraints in terms of the star-planet interaction models. Yeah, I'm really also happy to hear that you have observed the DS stuck.
Yes.
Because from August 1st to 15, we're going to have this 2-week multi-wavelengths campaign with 6 telescopes. And it will be nice if you can join us for that. Yeah, we'll talk about that later. But the one question that I have is this about the EUV versus X-ray.
Yes.
So I don't know if you've seen our recent paper by Namikata, where we looked at the EUV flux, XUV, basically characterizing as a function of the magnetic field, the total unsigned magnetic flux, because EUV and X-ray are driven by the dissipation of the magnetic field.
Absolutely.
And that's why they are strongly correlating, at the level of over 90%, with all those fluxes. And what we found is that the EUV, at least for solar type stars, I would say, and which are pretty different from M dwarfs, so we need to be kind of very careful here.
That's why I was very careful with sort of stating what our extrapolation was, because we have one solar type star and we're trying to estimate this for M dwarfs. Yeah,
but we found that the EUV flux is correlating with X-ray to the power law of 0.95. So that means that ratio is basically constant, at least for solar type stars.
Or at least a little bit closer than we found here.
Yeah.
That's interesting. Need to look at that paper further. Let's definitely chat.
Definitely. Thank you.
Thank you.
We have a question in the chat from Michael Way. You mentioned that XUV-driven planet stripping possible at later ages than thought. Can you guesstimate how much later for a TRAPPIST-1-like star?
I would need to run the numbers in short. And it's going to be very dependent on a bunch of different factors in terms of what you assume for the core mass versus the envelope mass. That's definitely going to be relevant, because that's what's speaking. If I go way, way back, find it. What's happening here with KT100 really is that for the much lower mass cases, you have a much smaller core mass, and so the gravity well's a lot. It's not quite as deep, and so that's why you're able to strip planets at a much later time. But off the top of my head for TRAPPIST, I wouldn't like to guess. Unfortunately, it's definitely going to be a strong function of whatever the core mass is.
Yes, thanks. Yeah.
Thanks, nice talk. Is NICER useful for X-ray transit?
If NICER is the one I'm thinking of, then we were looking into NICER a little bit a few months ago, and I can't remember exactly why we ruled it out as a
A high background, maybe?
Yeah, I think it was
Okay.
a high background, or the spatial resolution wasn't great. I don't remember exactly what it was.
Okay.
Yeah.
I had a question. In the Praesepe cluster plot, yeah, is the orange line pointing out any features?
Right.
there?
Yes. Sorry, I should have explained this a little bit better. So well, let's go through what the three lines are. So the red is the approximate position of the lower boundary of the radius valley. The blue is the Mesa 2016 Neptunian desert, and the orange line is another different definition of the lower boundary of the Neptunian desert from Owen and Lai 2018. They have a bunch of different boundaries based on the core mass, again, because that's, as I say, that's really relevant. And so for the smaller core masses, the boundary's a little bit lower.
So great talk. The only thing I know about stars is that they're bright, so I don't know what I'm talking about. But if you go to the transit, the W-shaped curve, is there anything that could suggest that, you have your model where it's radially symmetric, that the leading side of the actual corona is just stronger than the trailing side? I don't know if that makes sense.
In
Like
that
based on the star's
case,
rotation.
you'd expect one of the dips to be much deeper than the other,
Ah, okay.
which within the uncertainties that we have here doesn't appear to be the case.
Gotcha. Thank you.
So I have a question regarding this slide, actually. Do you have a plot for, so it's from 0.16 to 65 keV, right? So do you have a plot for the higher, the harder
Yes,
part of the spectrum?
We do detect the transit in there, but the light curve in general is a lot noisier. There's a lot less signal to play with within there, and so the transit's a lot out. We do have those. We do have that plot, and I can show you afterwards. But it doesn't look anywhere near as good as that.
So the point is that this system is particularly interesting because the distance to a planet is only around 6 solar radii, something like that. Yeah, it's 0.03 AU, which is about 6 solar radii. That's the outer corona of the star. So the planet is transiting. Is basically, that is within the coronal region of the star. That's by itself is very interesting.
Which is why interaction of the stellar and planetary magnetic fields, strongly is potential.
Thanks.
We have another question about this slide online from Michelle Silverstein. Can you remind us what the 3 different circles are in this schematic?
Oh, right, yes. So, where's my mouse? Okay, so this is just the big circle is the disk of the star itself, which is why, so the color is showing the intensity of the emission, which is, as I said, greatest around the edge of this disk. Here in the smaller circle is actually the planet itself, and then the slightly bigger circle is our best fit absorber. Obviously, in reality, this planet itself is blocking some as well. So this model needs, if you want to model this a little bit better, you want to somehow factor in the fact that this planet as well, potentially, these two aren't overlapping perfectly as
Yeah, I was going to ask, is there, is this like really idealized and you'd expect some kind of like tail feature as well, or is it truly like all of the absorption is ahead of the plane?
Depends what's doing the absorbing, right? I mean, if there's some sort of tail, you would expect this to be a lot less symmetric than it appears to be, right? If we go back to the Lyman alpha transit for GJ436, so the optical transit on here is this very small shaded region. This transit lasts for 20 hours after the optical transit finishes, and so you have this very sort of asymmetric shape to the transit. We don't appear to see something like that with the X-rays. This tells us that we're not probing any tail to any great degree.
Michelle just wanted to clarify, what is the absorber if not part of the planet? This again.
Well, say it could be material that's been stripped off the planet and is no longer bound to it. As I say, it could be in some way related to where the magnetic fields of the two objects are interacting, and that's maybe locking up a lot of material in one region. Maybe it's where, as I say, the lower velocity gas that's been removed from the planet that hasn't necessarily been accelerated yet, maybe that's where it preferentially builds up. There's a couple of different.
So you have 17 transits or 14?
This
Yeah.
is 20.
20. Have you explored the potential for time variability? I'm not sure if I'm mixing up the two most famous hot Jupiters, but I think this one showed Lyman alpha variability in the transit.
Yes, it did, and that was possibly linked to an X-ray flare that happened just before one of the Lyman alpha transits. We have at one point looked at it, and we clearly didn't see anything because I don't remember it. Seeing any variability, because the problem we have is there's just so much noise. You can still see it in the outer transit.
Right.
That it's difficult to tease this. I don't remember there being, when we've looked at this, significant variation if you split them up into like 2 or 3 different bins or say.
Yeah. Well, do you think we'll access, like, what's our next best opportunity for, you know, significantly improving the precision on something like this?
Convincing the XMM TAC to give us AU MIC time, because the star in that case is an order of magnitude brighter, even though the planet is a little bit smaller. That's probably our best immediate check. We also, one of my undergrads is currently looking into what AXIS is capable of in terms of observing X-ray transits, and estimated what the count rates should be for a bunch of nearby stars, and now we model it with some assumptions on the transit depth and can we detect anything with AXIS? Hopefully in the next couple of months be able to. But it's not going to be hundreds, obviously, right? At most, it's going to be a handful. At most. Really difficult to do this.
Any other questions in the room? Any more questions online? Not seeing any. Oh yeah, go ahead.
Yeah, I'm just trying to understand this enhancement at the center at the orbital phase 1. So in 2020, we looked at all data from Solar Dynamic Observatory, Sun as a star, and found one case with Shinturi-Yumi when the star spot was transiting the Sun in the equatorial plane, equatorial region from the one age to another age for 4 days. And we found a significant enhancement when the active region was at the center of the Sun. So basically matching this. So we can use this, the data. It's not model, it's data for Sun as a star, yep, to derive, the transit excluding that active region, because we know how enhancement works. So we have the basically transits in optical, in EUV, and in X-rays. It's all bands. So
that'd be really interesting, because that point in the middle has been a sort of puzzlement for us as to
what. Oh yeah, well that's for sure. That this middle is the contribution from a large active region, from X-ray emission, from steady state emission. Yeah. Thank you.
Okay, I'm not seeing any more questions, so we could wrap up there. Thanks for some great discussion. Let's thank George again. And thanks to everyone who joined online.
Everyone.